Hi everyone, my name is Nadav and I work as an engineering director at Meta. My team builds the native compilers and low-level libraries that drive our data centers. I'm here to talk to you about running a data center performance campaign. This topic is vast, so I'm specifically going to focus on one area, which is the efficiency of our software stack. Over the years, I've gotten to work with a lot of smart people. I learned cool things and had a lot of fun. I'm here to tell you about some of the things that I've learned. Building high-performance systems is fun, but it's also very important. 2/3 of humanity uses the internet, and internet companies provide important services. They allow people to connect with family, get work done, and learn new things. But it takes many computers to provide services to so much of the world. Internet companies build huge data centers all over the world. These data centers take a lot of power to operate, water to cool down, and material to build. Around 2% of the world energy consumption is spent on data centers. When we optimize some microservice by 1%, we allow our service to support 1% more users, and we need to build 1% fewer machines. Improving the efficiency of our software stack can save a lot of money, but it can also help reduce our ecological footprint. Today, I'm going to talk about a few things. I'll start by describing a few techniques for finding opportunities for optimizations. I'll cover the 5 categories for performance optimizations, and I'll finish by talking about a few performance challenges and ways to overcome them. This talk is for people who are interested in performance. It's not a tutorial for a specific tool, but rather a high-level description on how to approach a performance work at a data center level. I'll try to convince you that there are principles that show up at different levels of the stack, and that working in an organized way as a team towards one goal is the way to go. Okay, let's begin. So we know that it's important to improve the efficiency of our data centers, but where do we start? Well, back in 1960, Gene Amdahl was an engineer who worked at IBM. He came up with a simple way to predict the theoretical speedup of optimizations. His idea was kind of simple. The impact of your work is proportional to the size of the problem that you're solving. This is Amdahl's law. You should only optimize programs that consume lots of resources. This means that we need to find the slow parts of programs, where slow, according to Amdahl's definition, means that improving these parts would improve the overall system performance. But how do we do that? How do we find the slow parts? Typical programs contain millions of lines of code, and they run on complex systems in big data centers. This complexity makes it difficult to find opportunities for optimizations. There are 2 ideas that can help us make progress here. First, we need to look at efficiency at different abstraction levels, from instruction level to server utilization. There are opportunities at every level of the stack. The second idea is that we need to view this as a debugging exercise. In many ways, finding opportunities for optimizations is similar to debugging. In both cases, we never fully understand the behavior of a complex system. We use tools and experiments to get hints that direct our attention. In both cases, we're trying to reduce the search space and make it easier to find the problem. So let's talk about a few techniques that can help us find opportunities for optimizations. The first approach is really easy. Don't accept slow code. We said that it's difficult to find slow code, but it's really easy to find the problem if you know that a specific commit made things slower. This reduces the search space. Many teams measure the performance of some benchmark before they accept the new code. In the left picture, you can see a GitHub bot on the Swift project. The bot posted the performance report for a specific pull request. On the right, you can see a similar performance report from the LVM project. The colors indicate a change in the performance. Comparing the before and after runtime of a specific commit is a great way to keep the slow code out of the project. It's also important to track performance over time. This will allow you to look at the long-term trends. But more importantly, you'll be able to explain to other people what you are seeing. The picture on the left shows one of the benchmarks on the LVM performance site. It looks like someone made a change that made things slower. They got yelled at, so they reverted the change and things got back to normal. On the right, you can see a picture from the WebKit performance tracker. it looks like their performance effort is going well because the benchmark score improves over time. Okay, this was easy. From this point, we'll talk about things that require a bit more effort. Many of you are familiar with profilers. On the screen, you can see two profiler reports. On the left, you can see Linux Perf, and on the right, you can see Xcode instruments. Both of these tools are sampling profilers. They stop the process every few milliseconds and record the current stack trace. People often use flame graphs that you can see on screen to visualize time breakdown in programs. Profilers can tell us where the program is spending time. You don't know if the code is slow, but it's a good starting point for your investigation. Finding where time is spent on a single machine is nice, but it's not enough. Companies like Meta, Google, Amazon, and others built distributed profilers that collect and aggregate data from all of the machines in the data center. They simply combine the samples from all of the programs into a single database. This is very powerful because then you can answer questions at a different scale. Let's see how people use distributed profilers. In 2015, a group of researchers published a detailed analysis of the Google data center. They used distributed profilers to figure out what kind of programs are executed and where time is spent. One of the interesting findings of this paper is that their cloud had a flat profile. This means that no single program dominated the execution time. In the picture, you can see that the largest service was using fewer than 10% of the fleet cycles. According to Amdahl's law, though, this would be bad news because it means that there's no one program to fix to improve performance. The researchers also found that programs from different domains did similar things. Collectively, programs spent 5% of their time allocating memory and another 5% in the compression and hashing of data. You can see that the low-level C functions, memset and memcopy, are also used extensively by all programs. This opens a new opportunity for optimizations. These are what we call horizontal optimizations because they affect all of the programs in the fleet. Large cloud vendors have dedicated teams that are responsible for optimizing each one of these layers. At Meta, we have teams that develop high-performance libraries that accelerate different layers. JEmalloc is our fast memory allocator. Z-Standard is a state-of-the-art compression algorithm. We have Folly, which is our C++ library for containers and efficient data structures. We're also investing in the C++ standard library. In a paper from 2020, Meta engineers describe their top 7 microservices and show where time is spent for different kinds of tasks. On the left, you can see the time breakdown for different services. On the right, you can see something even more interesting. This is the time breakdown of the C++ library. You can clearly see that the web microservice is spending a significant amount of time accessing hash tables. This is pretty cool because now we know which functions or data structures we need to speed up in order to make this specific microservice go faster. This analysis is made possible thanks to distributed profiling. I've talked about 2 different kinds of optimizations. Vertical optimizations, where we optimize a single program, and horizontal optimizations, where you optimize a library that improves many programs. Horizontal optimizations are usually smaller, but they lift everything. When your profile is flat, it becomes difficult to improve things with vertical optimizations that target specific programs. And that's where horizontal optimizations come useful. You need to invest in both horizontal and vertical optimizations, but it's better to start with vertical optimizations. Okay, so we talked about distributed profilers and how they're useful. Let's get back to talking about different ways to find opportunities for optimizations. Another cool technique for finding optimization opportunities is called competitive analysis. It's not always possible, but if you can compare your project to a competitor, then you might be able to learn something. This is a picture of an old benchmark that compares the speed of programs that were compiled with 2 different compilers. It looks like one of the compilers did a better job on one of the benchmarks. This is great because now we know where to look and we can learn something. This is a good example of a way to reduce the search space and focus our effort. Profilers are great at finding where time is spent, but in some cases we might want to answer a different question, such as who is allocating all of this memory, or why are we sending tiny packets? There are tools that can answer these questions. Many of the modern tools are built on top of eBPF. eBPF allows you to write programs that collect information about the system at different levels. I recently wrote a tool that attaches to malloc and free and finds short-lived allocations. These kind of tools are amazing. They allow you to learn so much about your system. Brendan Gregg and other performance experts wrote excellent tools that you can download today and use. There are also excellent resources online that you can learn from. Another interesting idea that's good to know is the Roofline model. Engineers often like to compare their work to the theoretical peak performance of the machine. It's useful to know if we are running at 90% utilization or 20% utilization. Comparing the current performance to the theoretical peak can give us an important signal when we're trying to decide if we should optimize some code. Let's take a look at a quick example. Let's assume that we're trying to multiply two square matrices of 2000 by 2000. We know that matrix multiplication is n to the third, so the cost of multiplying these matrices is 8 gigaflops, where flop is a floating point operation. Our CPU has 4 cores, 2 execution ports on each core, and each execution port can do 8 wide vector fuse multiply add. The CPU is running at 3 gigahertz. When you multiply all of these numbers, it means that we can do 192 gigaflops per second. If we divide the cost of the problem by the capabilities of the machine, we'll get the time it should take to finish the job. In our case, 24 matrices per second. It's a good way to estimate if our implementation is efficient. If we are multiplying less than 24 matrices per second, then we know that we can still improve our implementation and get closer to the theoretical peak. To summarize, we can do some basic math to figure out if there's potential for speed up. Now, let's try a different approach. Modern systems are complex and they come with different options and configuration switches. I'll give you a few examples. You can tune your Java virtual machine by configuring the garbage collector frequency and number of GC threads. You can configure your CPU setting, your compiler, your kernel, and different libraries. What is the probability that all of these parameters are optimal for your specific microservice? Over the years, I've seen enough examples of configuration changes that led to significant performance wins. So it's a good idea to play around and change different parameters and see what works. Just play, experiment, and measure, and maybe you'll be able to land a performance win. I mentioned earlier that it's important to look at utilization at every abstraction level, but until now we only looked at host level performance. So let's zoom out. This paper from 2018 describes the utilization of servers in the Alibaba cloud. According to this paper, their cloud is not fully utilized. Jobs are not scheduled in an optimal way, and many of their servers are idle. They give a few explanations for why utilization is not high. One explanation is that jobs are not spread evenly throughout the day. Another explanation is that some services prepare for a worst-case scenario with a high watermark for resource utilization. In a paper from 2017, engineers from Meta explain how they use off-peak spare capacity for offline tasks, such as machine learning training. This is a good example of improving efficiency at the system level. So we talked about a few techniques for finding opportunities for optimizations. We've looked at a few layers in the software stack, and we talked about ways to reduce the search space, and we mentioned some tools. Now, let's talk about different kinds of optimizations. All of the performance optimizations in the world fall into 5 categories: algorithmic optimizations, eliminating redundancy, parallelization, batching, and ordering. The first category of performance optimizations is pretty straightforward. It's also the most important kind of optimization. Use data structures and algorithms that are efficient. Use quicksort instead of bubble sort. You get the idea. The second category of performance optimizations is also pretty simple. Don't do work that you don't need. This means a few things. Deleting code that you don't need, implementing local optimizations, hoisting things outside of loops. This category also includes things like zero copy data movement. On the screen, you can see an example that I found on GitHub. This code was made faster by removing some logging code that nobody needed. This is not hard. Let's now look at the next category of performance optimizations. Doing several things at once is a good way to make things go faster. This principle is used in every layer of the hardware and software stack. CPUs run different tasks on different cores and ports. GPUs are efficient because they operate on large vectors in parallel. At the circuit level, pipelining is done by placing flip-flops between arithmetic operations, making each one of the parts operate independently. At the data center level, we can split traffic and work between different hosts. Parallelism is used at every level of the stack. Fundamentally, when you have a multiplier, you can only use it once per clock cycle. So if you want to do more work, you need to create more multipliers, and the software needs to use these multipliers to get the work done. You can also parallelize the waiting part. Keeping several network connections open allow you to overlap the latency of the connection. This is concurrency. Just like parallelism, concurrency is used in all levels of the stack. Out-of-order processors hide memory access latency with concurrency. Efficient neural network implementations take parallelism to extreme. People parallelize work on multiple dimensions, within the input batch, between operations, within operations, in tiles and SIMD. This is possible because the work is so regular and there are few dependencies between arithmetic operations. Parallelism and concurrency are fundamental to performance at every level. Now, let's look at the next category. In many cases, we need to pay for some overhead for each operation. Batching allows you to amortize the cost over multiple operations. For example, TCP/IP packets have headers. When we send tiny packets, we pay the cost of headers again and again and again. When we batch data and send jumbo packets, we reduce the total cost of the headers. Okay, here's another example. You don't want to write data to disk too frequently because spinning the disk is expensive. So you should buffer the data in memory and save it less frequently. Okay, the last example is batching and matrix multiplication. The naive 3-loop implementation is inefficient. High-performance implementations fetch blocks from memory and use them to compute a tile. So they pay for the cost of loading data from memory just once. This is a form of batching. In many cases, batching also unblocks parallelism. Now that we've covered batching, let's talk about the last kind of performance optimization. The last category of optimizations is the most interesting. Ordering of data can create sharp histograms and efficient data access patterns. This is not an optimization by itself, but it creates opportunities for the other kinds of optimizations. Let's look at a few examples. First, we can arrange our data to allow efficient access patterns. In the game industry, people call this array of struct versus struct of array. And in the machine learning world, people talk about tensor layout. The idea is the same. Certain memory layout provide faster access patterns. But this is not all. The other powerful idea is that we can create sharp histograms. The bolt binary optimizer sorts the functions inside an executable according to how frequently they're executed. This creates a sharp histogram where all of the hot code is located in one place. This reduces cache misses. The picture on the screen shows the sorting process and how the sorting process improves locality. At a data center level, one way to create sharp histograms is to partition the work based on the kind of traffic. This helps to improve cache utilization and improve things like JIT compilers that get to look at different parts of the code for different machines. When dealing with data, compressing columns in databases is better than compressing rows. The reason is that columns contain one kind of data, like phone numbers or zip codes, that have a sharp histogram and compress better. There are many other examples of how ordering can help performance. So disaggregate, defrag, sort, reorder, because this will create sharp histograms and efficient data access patterns that will enable other optimizations. These were the 5 categories of performance optimizations: algorithmic optimizations, eliminating redundancy, parallelization, batching, and ordering. Next, we'll talk about a few topics that come up while optimizing code. All performance campaigns follow the same progression curve. At first, it's easy to find wins because this is the first time that someone is looking at a problem, and there are many low-hanging fruit. Afterwards, it becomes more difficult to find opportunities. You need to start putting more effort, and the wins are not that big. Eventually, you get to a point where it takes so much effort to make progress that it's not worth doing. In other words, performance work is asymptotic. You approach a plateau. The same team that in year 1 landed massive wins will make significantly smaller wins in year 2, 3, and 4. Another interesting topic that I'd like to mention is measurement noise. At first, it won't matter much, but eventually the size of the optimizations that you'll try to land will approach the size of the measurement noise. If you're trying to land an optimization that you think might bring 1% and the measurement error is around 1%, then you won't be able to distinguish between the noise and the actual win. Measurement noise is a big problem, and luckily there are a few things that we can do. The first thing that you need to do is you need to stabilize your system. Turn off turbo, hyperthreading, turn off address space layout randomization, eliminate other sources of randomness in the system. This will help. You can also isolate a small part of the system and measure only that part. The problem is that your benchmark may not represent the actual kind of constraint that the system has. Another thing that you can do is you can try to increase the number of samples. According to the law of large numbers, the average of many samples should eventually get close to the true average. If you keep measuring enough time, you will get a good estimate. The problem is that this becomes expensive very quickly because you will need to increase the number of samples exponentially to reduce the noise. Reducing the error by a factor of 10 requires 100 times more samples. So measurement noise is not something that you can solve, and you need to find ways to live with it. One of my favorite engineering quotes is by an economist, Thomas Sowell, who said that there are no solutions, just trade-offs. If you're building a system, then you need to consider the cost of benefits of different alternatives. Performance optimizations make systems more complex and fragile. I'll give you a quick example. Profile-guided optimization, or PGO, is a very effective compiler technique. It works by letting the compiler optimize code with information that's collected during the program execution. Knowing which part of the program are executed frequently can help the compiler make better optimization decisions. PGO can make your code around 10 to 15% faster. This is great news, but applying PGO in production is difficult. The natural release cycle of build a binary, package it, running in production doesn't work with PGO. When you use PGO, you need to allocate some portion of your data center to running instrumented binaries. You need to maintain a database with samples from different binary versions. You need to recompile a binary with the same version of the source code that you use for profiling. The software release, operations, and debugging all become more difficult. PGO is a perfect example for the trade-off that you have between performance optimizations and complexity of the whole system. I mentioned engineering trade-offs for a reason. During the development of the F-15 fighter jet, one team added a 20-pound built-in maintenance ladder to the airplane. When you increase the weight of the airplane, you also need to carry extra fuel to maintain the flight range. The total impact of the additional 20-pound ladder became 200 pounds in total. Eventually, the ladder was removed. Let's keep this story in mind when we develop software. Performance, complexity, memory usage, binary size are all shared resources. They're not owned by one person, they're owned by the whole team. Successful teams communicate, debate, negotiate when dealing with shared resources. When you run a performance campaign, it is especially important to work as one team. I'd like to take this opportunity and invite researchers in the field of systems to look at some of the problems that I mentioned. First, we need better programming languages. C++ is complex and it does not encourage safe coding practices. It's not only memory safety, it's also performance bugs. People forget to pass arguments by reference, and C++ inserts copies for them. There are also other issues. C++ has strange TBAA aliasing rules that prevent the compiler from optimizing things. And current C++ implementations don't have a high-level IR for high-level optimizations, and this leaves some performance on the table. Second, we need to continue to improve observability tooling. Maybe some of the techniques that people use in the security industry for things like intrusion detection can be effective for performance tracking. Third, we need to simplify the PGO pipeline. We need to simplify the DevOps of large-scale PGO deployments. The goal is to make PGO deployments as easy as deploying JITted code. And finally, we need to make progress on finding a methodology and tools around large-scale measurements and A/B testing in data centers. I hope that the research community will take on these challenges and help us improve the efficiency of data centers. Okay, finishing up. There are many smart people who work in the field of systems, HPC, compilers, architecture, and many of them, of course, write papers, blogs, books on the topic. On this slide, I included a few excellent books that I recommend. Improving the efficiency of software that runs on data centers is very important, not only for saving money, but also for reducing our ecological footprint. There are different techniques for finding slow code. One thing that they all have in common is that they reduce the search space on different dimensions. You also need to look at every abstraction level, from instruction to server utilization. We talked about the 5 optimization principles that show up at different levels of the stack. Amdahl's law dictates the rate of progress and resistance, and we can never escape it. You need to work in an organized way as a team and think about the consequences of your work. And finally, the goal is not to be perfect, but to get better over time. Thank you.
Thank you, Nadav, for such an awesome and principled approach to performance management at the data server level. It's a really thorough and very rigorous approach. I really enjoyed it. I've never actually have so many, clearly communicated bullet points for how to manage performance at a large scale. So really appreciate it.
Thank you, Taos. Thank you for inviting me. I really enjoyed recording this talk.
I hope everyone else has enjoyed it as much as I did. I really liked it. So I guess while we're waiting for other questions, I'm gonna start. So I was wondering, so I remember back in the day, there was this move for theorem provers that they are going to help us to, verify everything that is correct and blah, blah, blah. But there was a lot of resistance. And I think we started to employ more interactive approaches where we have interactive theorem provers that instead of just doing everything for you, they work with you to achieve the outcomes that you're looking for. So I wonder if you think that maybe at some point we're going to have maybe interactive compilers so that they work with you as you develop your software, and they immediately tell you, for example, oh, here you're actually leaving some performance on the table because, for example, we cannot prove that your operation is associative, or you have branching, or you have something else, and they tell you like, oh, but you can do this and that. So have you thought about this, or have you played with some of the approaches like this?
Yes, I love this question. But let's start from the beginning. So I think that compilers are already doing giving some feedback at a very basic level. For example, vectorizers would give you remarks when they can't vectorize a certain loop. I built the LVM vectorizer, and this is one of the features that we built around, I think it was almost 10 years ago when we developed the LVM vectorizer. It would tell you when it can't vectorize a certain loop if you're using a pragma. But we can do a lot more. Here's an idea. Let's say that you're making a function call. You're calling some function in your code, and the result of the function is used deep inside some if statement. Well, the compiler can't really sync the call into the if statement. But what if it can look at some profile information and say, hey, the call outside is used very frequently, but the value that's calling is not read very frequently. So emit a warning. So you could take this one step forward and rely on profile guided information and that you record at runtime to emit warnings. This is not something that's been done before. This is something that I would love to see being done. And there are other examples where I know that there was, there were different works on performance sanitizers and static analyzers for emitting performance warnings. Yeah, I definitely think that this is an area where researchers from the field of systems could step in and implement these things.
Yeah, that's a bummer. I believe performance sanitizer was actually scratched at some point, like a few years ago. So it didn't end up as productionized as other sanitizers, which is a bummer. I was looking forward to it. And I remember when Apple was doing the presentation on LLVM meetup about the remarks, and I saw that, oh, this is so awesome. Like you can see the source code with all these remarks. And I was like, why do we not have this in our code review tools? That sounds like a super useful feature to have. And like, it's such a bummer that we don't have it. So, and in general, I actually believe that, I guess it's just a reflection of how we frequently think about the systems, where we think of them as something like in stages where you write code and you deploy code. It's like phases, so it's phases. Instead of like a feedback loop where you have continuous flow of the information, just like when you have machine learned models where you continuously feed the data back so that you can update the model and produce better results, and you have the singularity like loop. Since you worked on both ML accelerators, so I guess much closer to ML, and compilers and so many awesome things, so do you see some progress around changing this our development methodology to more like a machine learning type of deployment procedure?
Yeah, so in a way, profile guided optimizations is similar to the training loop that you have in ML. And in both cases, it's difficult from an operations point of view. I mean, the concept is simple. You train the system and then you use it to modify the system. But it's really difficult from an operations point of view because you don't have one arrow that's going forward. You have the arrow going back, and then what happens when something breaks, and how do you handle multiple versions of the thing you're optimizing? Yes, and it's useful in some cases. I mean, it's worth the investment in some cases, and it's not worth it in other cases. Yes, it's interesting, and also so specifically for. So it's not exactly what you asked, but it reminds me of machine learning in compilers, which is something that's been, I remember reading papers about this maybe 15 years ago. There was the milepost project for GCC where they tried to apply machine learning to compilers, and there were works before that for doing code layout with decision trees in 1999. But somehow it never made it to the mainstream of compilers, which is something that I mean, it's a hard problem, but it's something that I would like to see. You know, after 20 years of research of applying machine learning to compilers, you know, somebody has to succeed and get it done finally. I don't know why it hasn't happened.
I believe I've seen some very recent papers on productionizing ML. I think Google wrote some paper on using ML for compilers very recently. I think they use it in CLN. So I don't know if I mean they report some good results with it, but again, I guess until everyone else is using it, it's probably not mainstream, and I'm not even sure if everyone is gonna trust it because it's like a black box thing.
You know, we have 2 decades of excellent papers with that report good numbers, but it's still not used mainstream.
And I think there is like a compiler AI or something like that also that is specifically aiming at like, using machine learning techniques for compiler optimizations. But again, it's not mainstream, which is such a bummer.
Chris Cumming, he built the AI gym. Yes.
So I guess, what are you most excited about in the near future? Like, what do you think is going to be, not just something that is going to be a topic of the paper, but actually something that's going to help us in practice in the near future?
Okay, so I listed a few things. One is programming languages. We need better programming languages. I mentioned the shortcomings of C++, which is now the most popular language for system design. So I think that now would be the perfect time to take everything that we know and tell it to the designers of the Rust programming language, so that they could take these lessons and make sure that Rust is well positioned for performance work. We also need to improve observability tools. That's a second topic. I feel like we're still using profilers and basic debuggers, and we should have better tools. eBPF is a huge step, but we should. I'm sure you can build cool things on top of it. Simplifying PGO. That's also simplifying the DevOps of optimizations. This is also very important. There was a fourth point that I forgot, but
this is awesome. But it's just I only worry a little bit in terms of languages. It seems like we're actually getting into the fragmentation area, because Google just recently announced Carbon language that's going to be the future of C++, and then there's obviously Rust and so like Zig and so many, and I just feel like it's one of those like CDC comics where today we have 12 standards, like we need to fix that.
N+1.
Right. So that's why I just hope it's not going to be like that.
So when I look back at the history of programming languages, I mean, you can see that every 5 to 10 years, there's a new major programming language. Like you see, just by counting, I mean, you have modern programming languages for about 40 years, and then I can count Java, C++, Go, Python. So if you just divide the number of languages by this time scale, you'll get to a new major programming language every 5 to 10 years. So I know that somebody in the next 5 to 10 years will invent a new programming language, and we have to give them feedback so that they make the right design decisions.
Yeah, definitely. And actually, that's a great thing for collaboration, because in Rust, for example, probably the biggest feature they have is linearizable types, which comes from the theoretical stuff. It's actually one of the very simple things. Like the borrowship, like borrowing semantics, is very simple in terms of the type theory. It's pretty much a basic primitive, but it wasn't used pretty much in any other language. So it's probably a great reason to collaborate for all of us more and develop these things.
Now with Rust, I'm still on the fence. I recently talked with Patrick Walton, and he mentioned to me that, and I mentioned this in the talk, that the Rust aliasing rules are more strict, and it allows the compiler to make better decisions compared to C++, where anything can alias but then also Rust also encourages coding practices that may not be beneficial. So let's say that you design a data structure, you're not going to use pointers for a tree. You would use an array of indices. And then I found that myself, when I write some Rust code, sometimes it's easier for me to clone some array instead of fighting the borrow checker, and so this is not ideal. So on one hand, Rust is better in some areas, and on the other hand, we got to watch out for these anti-patterns that develop. Maybe it's just me. Maybe other people are better at writing high-performance Rust code.
No, I think it goes back to the quote that you mentioned about the trade-offs. I mean, it's all about the trade-offs. So I don't think there is the silver bullet that's going to address all the issues. I think it's all going to be up to us, which is, I guess, good for our job security.
Yes.
Well, thank you so much, Nadav.
Thank you.
Really appreciate your talk and your time, and hopefully we'll see you at the panel to continue our discussion in a broader setting.
Thank you for inviting me, and
Thank you so much
for organizing this conference. Thank you.
Thank you.